Okay, let's begin. Now, as has been announced before, every month, the last Thursday, you will have a quiz for about 45 minutes. So the first quiz of the course will be on 29th of August. Okay, so 15th August is a holiday. 29th of August, we will have a quiz and we'll have some extra lectures also going forward. All extra lectures will be online on Teams. Okay, so let's begin today. As you know, we have been doing part of speech tagging, and part of speech tagging comes fairly low at the NLP stack. And this actually is a feeder into subsequent stages in language processing. Now, when we make use of large applications of NLP, like machine translation, for example, or make use of a chatbot, or summarize opinions for, let's say, service by Flipkart or Amazon, then we are using NLP technology there. So when you're making use of these large applications of language processing, for example, you're using interacting with the chatbot, you must understand that lots of NLP technology is being used there. Any problem with hearing? Am I audible everywhere? Oh, okay. So the part of speech tagging or finding out the grammatical categories of the word is a very basic NLP task which needs to be done well. Okay. If part of speech tagging is not good, then parsing will be bad. The semantic roles will also go wrong. Finally, any kind of inferencing based on the text will go wrong. Okay. So last week, this is the one slide recap of what was done last week in the week of 5th August. We covered NLP stack with ChatGPT's performance at each layer. ChatGPT, as you know, is a large language model-based application. It is LLM-based conversational AI, right? Then we work with this to bank. I bank on the river bank. Okay, that means to carry out my financial transactions, I depend on the bank which is on the river bank. So the word bank has been used 4 times, 2 times as a verb and 2 times as noun, every time with a different sense. And ChatGPT has been able to disambiguate all the appearances of bank correctly. The disambiguation begins with part of speech tagging. The bank can be both noun and verb. So ChatGPT is able to produce the correct part of speech tag, which I showed last time, okay, through a number of slides. Then we gave the part of speech tag definition. What is the input? The input is a sequence of words, and the output is a sequence of tags or labels. Then we made a argmax-based formulation for the problem. We are going to make use of these all the time, quite frequently. And then we also asked, should we apply Bayes theorem? When we applied Bayes theorem, probability of T given W, where T is the tag sequence and W is the input word sequence, probability of T given W got transformed into probability of T, which is prior probability, into probability of W given T, which is called the likelihood. And there, by applying chain rule and Markov independence assumption, we got an expression which involves product of transition probability from one tag to another, and the observation probability of a word given the tag. Okay, so this exactly corresponded to a very famous machine which is called hidden Markov model. So we started discussing hidden Markov models, and this was a good match between the task and the technique. So we have to remember that in machine learning, we try to make use of a technique to solve a problem. Okay, what is important is the problem. The technique is secondary to the problem. The problem needs to be solved, whatever with the technique. Now, some techniques are natural for the problem. Some techniques are more efficient. Some techniques are very complex, but they deliver very well because the accuracy is very high. So for any technique, there are dimensional considerations which need to be kept in mind. First and foremost, possibly, is accuracy. Okay, how correct is the set of part of speech which is produced for the sentence? Then comes the question of efficiency. How quickly do I get my result? If I have to wait for the part of speech tag sequence to arrive after 5 minutes, then this will not be very useful. Okay. Then how is the complexity of the algorithm? Okay. So now if I make use of hidden Markov model, which is a very simple algorithm, but if I make use of conditional random fill, that will be a more complex algorithm. Okay. And then how easy it is to interpret that model. That takes us to explainability. So machine learning models which are based on neural networks are very difficult to explain because you do not know what is going inside the model. So there are various considerations which come into our mind when we think of a technique for a task. But the most important question is the technique-task mapping. Is this technique natural for the problem I am solving? Okay, so hidden Markov model, after the argmax formulation of part-of-speech tags, seem like a immediate, match, okay, good match between the technique and the task. So this is what was done in the last week, and I hope you have had access to the slides and the recording. Sorry, a bit, sorry about the slides coming a little late, and also the recording had to be redone because of internet problems. Anyway. So the NLP stack, as you can see on the right-hand side, passes through morphology, pause tagging, chunking, parsing, semantics, discourse, and so on. So at every layer, we could see that the chatgpt system worked pretty well. It could handle a complex sentence like to bank, I bank on the river bank. Now, one question that arose when we were discussing is that we apply the Bayes theorem and convert probability of T given W to probability of T into probability of W given T. The probability of W gets dropped because we are interested ultimately in comparison of the possible tag sequences. So should I apply Bayes rule or not? So I briefly mentioned in the class the case of cancer detection and visa application. So I brought some a little bit of discussion on this problem to go deeper into the question. So cancer detection versus visa granting, the two situations. The formulation is in terms of these posterior and prior probability and likelihood. So both the problems are of the form probability of B given A is equal to probability of B into probability of A given B divided by probability of A. So the right-hand side is the application of Bayes theorem on the left-hand side. Now, how is the decision in favor of cancer given? If the probability of cancer cancer is greater than probability of not cancer, of course, there is a conditioning part given the patient information. Then we say that the patient has cancer, and this inequality implies probability of cancer given the patient is greater than 0.5. Okay. Now, grant visa. If probability of grant visa given the application is greater than probability of not grant visa, that means again probability of grant visa should be greater than 0.5. Okay, this is the decision rule. Now, the key consideration is which data is more reliable for obtaining the probability. Since we are making use of probabilistic framework, we would like to know when we estimate probabilities from data. Okay, so which method or which direction, left-hand side or right-hand side, will give us more reliable probability values. Let's examine this further. So the posterior probability we're dealing with is of this form. Probability cancer equal to yes or no, that is the decision. I've written a shorthand here. Probability of cancer given the patient parameters. The patient parameters are, let's say, hemoglobin count, weight, family history, age, and so on. Prior probability is just probability of cancer, no conditioning there. And the likelihood is probability of patient parameters given cancer. So given cancer, we observe parameter values. So this obviously requires a sample of the cancer patient data. Now we go to, let's say, a hospital like Tata Memorial and take many cases of cancer patients and collect all these observations for those patients: hemoglobin count, weight, family history, age, and so on and so forth. Okay, so this likelihood probability needs a sample of cancer patients. Okay, and if these patients indeed have cancer, this set is extremely reliable if it is from a very high quality source. Okay, very high quality source. So this requires a sample of cancer patients and their parameter values. What is the question? No. What about this probability of cancer? This again will require a sample from the population. Maybe we are trying to detect, let's say, our population is, let's say, people who smoke. Okay, people who smoke cigarettes. Let's say this is our population. Okay, so we'll have to get a sample from the population of people who smoke. It's going to be a very large set, and we'll have to take a sample out of it. Now, from sample to population, how does the statistics behave? There is the topic of hypothesis testing, which we'll have to do in this course. So I hope you are clear about the parameters which are being used for decision making. Okay, we have three parameters: probability of cancer given patient parameters, either these or two parameters, probability of cancer and probability of patient parameters given cancer. Now we have to think which probability is more reliable, which probability can be obtained more reliably from data. Okay, there is no option other than going to data and getting these parameter values. So probability of cancer given patient parameters, we'll have to collect a large set of patient parameters, okay, and then see their level of cancer or not cancer. So after we collect all these patient parameters, okay, these cases of patients and their corresponding parameters, we have a set of label data which is cancer and not cancer. It is a binary classification problem. On the face of it, it sounds like a very simple proposition, and we should work with the left-hand side, most probably. Okay? But it depends on how easy and how reliably can we collect these data of patient parameters or people's parameters, and they're having cancer. Okay? And we have also, of course, the two other parameters. Now we go to the case of visa granting. The posterior probability here is probability of grant visa given candidate features, the application feature. So candidate features would be income, education, travel history, and so on. Okay? And also the field in which the applicant is. Some fields are difficult to get visa, or let's say for some countries. And the prior probability is probability of grant visa. How many applications were granted visa? How many applications were rejected? That data we have to obtain from some source. Okay, let's say we go to US Embassy and collect this data if they're willing to give this data. Then likelihood is probability of the candidate features given that the visa was granted. Given that the visa was granted. So again, we'll have to collect all these statistics. So if an applicant has been granted visa, what is the income? Okay, what is the income range? We take a look at that. So now what happens for this particular case is that the probability of income, probability of education level, probability of travel, etc., are obtained by making use of naive-Bayes assumption. Okay, many times we apply naive-Bayes assumption. Of course, there is a dependency of income with education, for example. Okay, but we make naive-Bayes assumption and we assume that all these random variables like income range, education level, travel history, they are independent of each other. And by making use of that naive-Bayes assumption, we obtain these statistics from the data. So this is the scenario in front of you. Now you really think deeply on which path to take. work with left-hand side, which is called discriminative modeling, or work with right-hand side, which is called generative modeling. Okay, it totally depends on how reliably you obtain these probability values. Okay, think about this question. I think the setting is quite clear to you. Now think about it. So I'm not taking any comments or questions right now. We can do this later. Let me proceed with the part of speech tagging discussions. Okay, so part of speech tagging, is pretty low in the NLP stack. It fits into chunking, which is formation of small phrases, and small phrases feed into parsing, which creates the deep structure of the sentence. Okay. Now, in this argmax computation, we have seen T star is equal to argmax over all possible T, probability of T given W, where T is the tag sequence, W is the word sequence. So we apply Bayes' theorem and obtain a probability of T into probability of W given T divided by probability of W. Since this maximization is on T, it does not depend on W, so PW can be dropped from the formulation. So we have probability argmax T, probability of T comma W. Okay, so this probability expression PT into probability of W given T, you can see is a joint probability. Okay, so there is a classic debate on which method is better, to work with conditional probability or to work with joint probability. Shall I work with probability of W comma T, or shall I work with probability of T given W? Okay, probability of T given W or probability of T comma W. Which one should I work with? So typically the number of parameters, typically the computational cost in joint probability is higher than the computational cost in conditional probability. Okay. Again, I leave it to you to think why this would be the case. Okay. In fact, to compute joint probability, you will have to make use of conditional probability as a step. Okay. So to work with the conditional probability or to work with joint probability, that gives rise to the question of discriminative modeling versus generative modeling. Okay. And why use these terms called generative modeling, discriminative modeling also is something we need to keep in mind. Okay. So let's proceed. So from this formulation, we got this transition probability expression, bigram probabilities, probability of Ti given Ti minus 1, and product of such bigram probabilities. They can be easily obtained if we have annotated corpus, right? We note how many times there is a transition from adjective to noun to obtain probability of noun given adjective. And the other formulation was, the other part of the expression was I given Ti. What is the probability of the word appearing at the ith position, where the tag at the ith position is Ti? What is the probability that we will see the word brown, having known the fact that at the third position we have a noun? Okay, what is the probability of obtaining that? So that is also very easily obtainable if we have annotated data, right? So our whole task of computing the best probability tag sequence boils down to taking the product of bigram probabilities and word observation probabilities, which is also called lexical probability. And this can be diagrammatically depicted in a nice way. We start with the starting of the sentence, which is hat, and then from hat we go to N, V, etc., and keep developing the automaton, which is probabilistic automaton, systematically from state to state. So note also the arcs which go out from one state to another, and the arcs which go from one state to a observation. So there are arcs going from, let's say, N to V for people jump, and there is an arc going from N to people to capture the lexical probability. So this is just a diagrammatic representation of the transition probability and observation probability. So these led us to adoption of a well-known technique, which is hidden Markov model. And when we make use of hidden Markov model, we note that this is an example which is many times used for illustrating the operation of hidden Markov model. The problem is as follows: we have three containers, okay, U1, U2, and U3, and each of them has 100 balls with a different distribution for the colors of red, green, and blue, right? And the problem is as follows. We pick up a ball with replacement from any container, okay, that is probabilistically decided. And after we look at the color sequence of the balls that we have obtained, what is the highest probability sequence of containers from which this observation has come? Okay, so this you can easily map to part-of-speech tag problem. All these R, G, G, B, R, G, R are what? Which we see in front of us. And the aren'ts are the part-of-speech tags. So this is a very artificial situation. There are only three tags. And that is sometimes used, in fact. Suppose we say that there are only three tags in the form of nouns, verbs, and everything else. Very interesting, noun, verb, and everything else. Okay, then this is exactly the identical problem. So, so this has some kind of linguistic viability, it seems. Suppose I say U1 is N, U2 is verb, and U3 is everything else. Okay? Then if we say the probability of seeing a noun after noun is 0.1, and seeing a verb after noun is 0.4, and seeing anything else after noun is 0.5, that linguistically seems realistic. Seeing a noun after noun is not very common, okay, except for compound nouns. Cricket bat, for example. In cricket bat, you're seeing a noun after a noun. But seeing a verb is much more common. Okay, John saw Jack, more common. So this table seems to be realistic, even linguistically. Anyway, this is given to us. We are also given the observation probability table, and we are given initial probability column, which container we are starting from. So then this transition probability table and the observation probability table are expressed as a finite state automaton. That is three states only, U1, U2, and U3. And the transition probabilities are recorded on the arcs. Observation probabilities are recorded on the arcs coming out of these states. So since we have to take the product of transition probabilities and observation probabilities, we can convert the previous diagram into this diagram, where we have from a state one transition arc going out. Okay, one transition going out for every combination. So this is transition and observation combination. So if we look at this R, 0.03, it means the probability of remaining in the state U1 and producing a red ball is 0.03. And, okay, so and means the joint probability. The joint probability is always expressed by a product, right? So this is the product which is playing its role here. So the hidden Markov model now has been expressed in the form of a finite state automaton with probability values. Any question at this point? How transition probabilities, observation probabilities are taken, and how they are used to create a diagram that is shown here. Any question? Okay. Now, towards the end of the last class, we remarked that there are three problems of importance when given in hidden Markov model. Given the observation sequence, find the possible state sequence. This is called the Viterbi algorithm. Given the observation sequence, find the probability of that observation sequence. That's called forward-backward algorithm. The probability of a word sequence is called language model. Okay. And given the observation sequence, find the HMM parameters. This is also called re-estimation or Baum-Welch algorithm. Okay. Yeah. Yeah. Come again, what is the question? Why do you say that? So I just have to draw one fictitious state. Okay. I have to just draw one fictitious state, and from there draw three arcs going into these U1, U2, and U3 with an epsilon transition. And the probabilities will be the initial probability values, which is not shown here. Okay, good. So that's fine. It completes the discussion. True. So language model, you see, is the probability of a word sequence. If this is the definition, what is the definition of a large language model? Acha. So we have three words, right? And it's an NLP class. So large language model. What is the part of speech tag of every word? Large is adjective. Language model. Okay, so when you model a phenomenon, there only is verb. Here it is noun. You are sure about this? Your model is a noun because of. Okay, fine. So large is an adjective. It qualifies some noun. So which noun? Yes, language or model? Model. Okay. So if model is large, and if model is a joint probability of a sequence of words, if model is that, and probability of a sequence of words is the model, so then you replace is the language model. Then you replace language model, the phrase language model, by this whole word sequence. Probability of a sequence of words. And before that, place large. Place large. Now large qualifies what? Visible, the board is visible from the back. So you are saying large qualifies model. And model is paraphrased as can you take this picture, write this, and give me a slide after? Again, let me remind you, it is an NLP class. Okay. So large language model, three words, part of speech is JJ. NN means noun part of speech. The word model is expanded into 1, 2, 3, 4, 5, 6 words. If this sequence of words, no, sorry. This is a paraphrase for these two words, language model. Now, if large qualifies this whole phrase, language model, then large must be qualifying this sequence of words also. Huh? Should be. Okay. If it is qualifying this sequence of words, then I know from my knowledge of grammar and language that adjectives qualify nouns. I'm acting like a machine learning classifier now. I'm a dumb classifier trained on some data. I have been trained since my childhood through my education and experience of language to learn that adjectives qualify noun. So large will qualify a noun in this sequence. Now I have to do part of speech tagging. What is the part of speech tag of probability? Probability verb? Noun, NN. First of all, you will have to do good NLP, and then you will be able to ask any machine learning model to do NLP. Okay, first you will have to understand language bits. So NN, what about of preposition? The tag is IN. In. What about A? A is an article. Okay, so it is DT. Sequence. Of is IN. Words. Plural noun NNS. Plural noun. Now I have done part of this speech tagging, and I know. Please be in the same mode as I am. You become an NLP machine. Okay, and then go through this NLP stack. I have gone through this NLP stack. I have done part of speech tagging. Now I want to establish dependencies. Okay. So first, so since adjectives qualify nouns, first candidate in its probability. So E is large qualifying probability. Is it large probability? Why not? Why not? Large probability, very close to 1. Now, ask Satyam to get up. Important discussion, please listen to it. Okay, so large probability, no. So adjectives don't qualify prepositions. I rule out this dependency. Sequence candidate. Large can qualify sequence. Of no. Words. Large words. How do you know? Why not? No, why can't large? I'm getting confused. Why can't large qualify words? What does large word mean? We have heard of long words. Have you heard of large words? So large words will be ruled out by a language model. This sequence does not appear in corpus. Very low probability. Okay. And otherwise, of course, you have to make use of semantics and say that how can a word be large? What can be long? Or maybe, it's the wrong use of language. Maybe the person means long word. That also happens sometimes. Okay. So the language model, which has good probability values, good distribution, will rule out large words. There is nothing called large words. Long words is. Large sequence, quite likely. Large probability is not very uncommon. You probably have seen it in corpus. This is large probability. So these also, so there are two candidates now: probability and sequence. How to choose between them? Probability, by lexical distance, the closer. Proximity is a disambiguator, yes. Hmm. But the answer will be large sequence. Okay, large language models deal with large sequences. So GPT-4 has in the conditioning part 400 words, 4,000 words. So large language model means probability of large sequence of words. That is the meaning. Okay, so clear to all of you what is large language model after all? We were assisted, okay, quite strongly by the definition of language model itself. Language model is nothing but probability of a sequence of words. And then you might come back and say, what do you mean by probability of a sequence of words? Never heard of such thing. Nobody told us in the school when we were writing, when we were understanding language, literature, etc. Nobody gave us any notion of probability of a sequence of words. Did you ever hear this before the class? Probability of a sequence of words? No. In fact, if you talk to linguists, grammarians, they laugh at this idea. What is the meaning of probability of sequence? Well, probability of a sequence of words always corresponds to the probability. What is this probability? Probability of the occurrence of this sequence in a corpus. Very definitely. Let's note, and you can also write this in the slides. So very deep things, right? Very deep things. And this actually sets the whole tone for statistical NLP. Probability of a sequence of words is actually probability of occurrence in corpus. I hope the words are visible from the back. Back? Are the words visible? Say yes or no. Visible? This side? Yeah. Yeah, you're right. You're right. You're right. So you're right. So LLM should be actually expanded as long language model. Okay, should be. But there is another angle to this. Large language model somehow has got tied up with a machine. Large neural network. You don't have long neural network. You have large neural network. Okay, so since this binding has happened, this strong binding has happened, the name has taken. Okay, so the probability of sequence of words is actually equivalent to probability of occurrence of that sequence in the corpus. Now, if that sequence doesn't appear in the corpus, we would say it is unlikely. Now, something interesting has happened after that. What has happened is that NLP has taken the view that anything which is very frequent in the corpus also has a sound meaning. Okay, so the text is meaningful. The text is not a nonsense if it appears many times in the corpus. Okay, this is a frequent-list approach, and this is some kind of majority voting, I would say. If a sequence of words, if a language object, it can be one word or multiple words, appears many times in the corpus, it probably has a sound meaning, not a nonsense. Okay, so then what will if you take that point of view, then you can see that linguistic creativity becomes a problem. Okay, how can a new piece of poetry be written? How do new words get coined? Now we have a very common word. Please Google that information. It's a new word. Okay, it never appeared before in the corpus. So first time it appeared, people thought it's strange. Then after that, by the force of frequent appearance, it acquired a meaning and a force of its own. Now Google is a very powerful word as a verb, as a verb. So is Facebook a verb? Please Facebook me. Have you heard this? No. So you'll be somewhat surprised if you hear this expression. But if it becomes frequently used, then it will go. It has gone into the language, and it will be in our consciousness also. Yeah, please WhatsApp me. Yeah, WhatsApp is a verb. Tweet me, yes. But I have not heard. Please LinkedIn. Why not? Something to think about. I will LinkedIn you. That means I look you up in the LinkedIn. Why doesn't it happen? Language seems to have a mind of its own, right? Yeah. So on this note, we'll take a break for. So just before the break, we are discussing the notion of large language model, and I said that large language models have been closely tied up with large neural network-based machine learning system. Okay. Am I in the meeting? No, I don't think so. No, I'm in the meeting. Sure, let's take it. I don't think so. I'm getting the signal of not being in the net. Is anybody on the Teams link from here? The class? We're hearing from this. Okay. So just before the break, we said that large language models are very closely integrated with large neural networks. Okay. And I would like to say this for you to think about that without neural networks, large language models would not have been possible. Think about this point. Okay. That without neural networks, large language models would not have been possible. And the reason for this is something called curse of dimensionality, which we mentioned one of the weeks before. Because of curse of dimensionality, without a neural network, a large language models would not have been possible because you will have to deal with exponential number of probability values. It's a good quiz question. So remember this one. Okay. Some question, comment, some difficulty? No. Okay. So now okay, so the computation of call stacks we saw last time essentially involves creating a search tree, okay, and navigating through the search tree to find out the highest probability path. So here the sentence is brown foxes jumped over the fence, and I would like to insist on you to make note of two guards for this kind of sequences. The first guard is in the beginning, which is a hat symbol. And the second guard is at the end, which is the dot symbol. The hat and dot symbols have the same level as the part-of-speech tag. And the in-between words have to have their tags as per the context. So brown can be both noun and verb, but in this context, noun and adjective. In this context, it is an adjective, so the second tag will be applicable. Foxes can be both verb and noun, but in this case, it is a noun. Okay, so that disambiguation has to be done. Jumped can be both a past tense verb and an adjective, but the past tense verb is applicable here. Over is a preposition. The over can have many parts of speech. Okay, then the is a determiner. Fortunately, it has a unique tag. There cannot be anything other than a determiner. But can it be? There can be only determiner, nothing else. Can it be anything else? I'm saying there can be noun. Hmm? What is that? Oh, the is used as a name. Somebody could have a name as the. In what way? The is a determinant, yes. The is a determinant. No, the is a determinant. Yeah, it is a noun. Okay. Then fence can be both noun and verb. And finally, the dot. Okay. So you can see that for every word, you have a column of possibilities. And once we raise these columns and create this diagram, it is called a trellis diagram. Okay. So trellis and hidden Markov model, Viterbi, they always, this terminology go together. So it's a trellis diagram. It becomes a tree, and we have to find out the best possible path in the tree, which will give me the best possible tag sequence. So the tag sequence. Uh, okay, so the probability of the path sequence is found this way. The probability of a path, for example, the topmost path will be probability of t into probability of w given e, which is probability of hat. See the first state, hat, into probability of nn given hat, into probability of nns given nn, into probability of vbt given nns, and so on. Okay, it goes up to the end, which is the dot symbol. That takes care of all the transition probabilities. This whole quantity has to be multiplied by probability of hat given hat, which is 1, probability of brown given nn, probability of foxes given nns, and so on. Okay, so that will give me the path probability. And this way, there will be an exponential number of paths, and we'll have to get the probability of each path and find out which path has the highest probability, and that is the answer. But that's a very inefficient method of finding out the best possible path, mainly because we are repeating a lot of work. So if you take the first path, then the probability of nn given hat is computed, which is used in computing the probability of the first path. In the second path also, where you have hat nn bbs, in the second path also same probability is used. So why should I compute it again? Okay, I just have to do a lookup of pre-computed probability of the partial paths and use it. So that is the essence of Viterbi algorithm. Let's move. So let's illustrate the Viterbi decoding for part-of-speech tagging. This example is from our book, which came out in 2023. So let me illustrate this with a very simple sentence. People dance. That's all. A very simple sentence. And what kind of ambiguity we are talking about here? People and dance can both be both noun and verb. Old people, here people is a noun. Township people with soldiers, here people is a verb. Dance also can be in both parts of speech. Rules of classical dance. Here dance is a noun. And will dance well, here dance is a verb. Okay, so both people and dance can be both noun and verb. Tag sequences, 4. Okay, noun, verb, verb, noun. So how does for simplicity, we take single letter tags, N for noun and V for verb. So we can have hat N dot, or hat NV dot, hat VN dot, and hat VV dot. These are the possible tag sequences. We know that out of these, the second option, hat n v dot, is the correct sequence. Now, how to get this sequence is the question. How do we get this sequence? So first of all, we create the trellis. The trellis is column of tags on each input word with transition arcs going from tags, which are states, to tags in consecutive columns, and output arcs going from tags to words, which are observed. So you look at the trellis here, we have the hat symbol, hat goes to hat. Then we have hat, from hat are going to V and N, with labels of probability of V given hat and probability of N given hat. Then from V, we have an R going to people. So this is the probability of people given V. Then from N, we have an R going to people. So this is probability of people given N. From V, we have an R, probability of V given V. From V, we have an R going to N. So probability of N given V. Probability of V given N, probability of N given N. Okay, so there is an X kind of pattern there. Again, from V, there is an R going to dance with probability of dance given V, and also probability of dance given N. Finally, we have probability of dot given V and probability of dot given N, and observation probability being probability of dot given dot. This completes the whole trellis. Though it's a very simple example, this captures the essence of a trellis construction. You can create a trellis for any length of sequence. Even if a sentence is 150 words, you can easily construct the trellis. Okay. So now, how do you get probability of dot given V? You find out how many sentences end in V and the total number of sentences in the corpus. Divide the first number by second number, you get this probability. So see the dependence on corpus. See the dependence on data at every step. Okay, so all these parameters which are shown on the trellis are obtainable from an annotated data. This is what you will do in your assignment also. The assignment will be due end of August. So our aim is to select the highest probability path. So from 4 possibilities, A's and B's are accumulated probabilities, let's say. Let us look at the diagram. So from hat, we go to V or, and we have the probabilities A1 and A2. How is A1 calculated? Probability of N given hat, the transition probability, into probability of hat given N, which is the lexical probability or the observation probability. A2 is probability of V given hat multiplied by probability of hat given hat, observation probability. Then from V to V, we have the probability V4, from V to N, V3, from N to V, V2, from N to N, V1. Okay, so V1, V2, V3, V4, because of the 4 possibilities there. So V1 is what probability? A1 into probability of N given N multiplied by probability of people given N. At the second position, I have the word people. Okay, so probability of people given N into probability of N given N, and all the accumulated probability, which is A1. V2 would be A1 into probability of V given N multiplied by probability of people given N. Because the state is N now. Then next, V3 is A2 into probability of N given V into probability of people given V. V4 similarly is A2 into probability of V given V multiplied by probability of people given V. Okay, all these is as per the theory, the way we have developed the argmax expression. All okay? All fine here? Okay. And you have to keep on accumulating probability. That is the heart of the dynamic programming system, or Viterbi. So far, I think you are still not seeing why the algorithm will not be exponential. Okay, the way we are proceeding, we are possibly going towards an exponential algorithm, which will not be the case as we will see. Calculations. When it comes to the start of the sentence, most sentences start with a noun. So let's have probability of n given hat as 0.8 and probability of v given hat as 0.2. And of course, probability of hat given hat is 1.0. So we are not making use of data. We are just making use of some linguistic intuition. Most of the sentences begin with n, so therefore it is probability of n given hat is 0.8. And probability of hat given hat is 1. Therefore, A1 is 0.8 and A2 is 0.2. A1 and A2, as you can see on the screen. So A1 is 0.8, A2 is 0.2. Okay, next. The transition from N to N is less common. So now we encounter people. We are dealing with hat. Now we are encountering people. And therefore, we need more probabilities. Transition from N to N is less common than to V. We would not have to do this reasoning if we had annotated data. We are doing this reasoning purely based on linguistic intuition. Probability of V from V as an auxiliary verb to main verb is quite common. For example, is going. V to N2 is quite common, as in case of a nominal object following going home, for example. Following plausible transition probabilities we can adopt for the purpose of discussion. Probability of n given n is, let's say, 0.2. Probability of v given n is 0.8. Probability of verb given verb is 0.4. Probability of noun given verb is 0.6. Based on our understanding of the language phenomena, how language operates. We also need lexical probabilities. People appearing as verb is much less common than it's appearing as noun. So let us have, and there are some more probability values. Okay. People appearing as verb is much less common than it's appearing as noun. So let's have probability of people given noun is 0.01 and probability of people given verb is 0.001, 1/10 the probability. It will be much smaller. Note, N combination, an example of that will be golf club, cricket bat, town people. Ambiguity. There is an ambiguity. The town people visited was deserted. Town people will not be able to live here. So you can see the ambiguity here. In the first case, town is a noun, acting like a noun. And in the second case, town is acting like an adjective. VV combination. Hindi has this kind of combination. It is rare in English. Of course, you have auxiliary main verb combination. Hindi has hasparna, for example, laughed suddenly. Bengali has chole gelo, went away. These kind of combinations you see in Indian languages. But in English, two verbs can come one after the other, only as auxiliary and main verb. Okay, let's proceed. So now we calculate the B's. These were calculated as 0.8 into 0.2 into 0.01, which is 0.0016. You can verify this from the slides later. Let me go through the calculations. B2 is 0.8 into 0.8 into 0.01, which is 0.064. B3 is 0.2 into 0.6 into 0.001, which is 0.00012. V4 is 0.2 into 0.4 into 0.001, which is 0.00008. Okay, so this is the set of probability values I obtained based on the parameters. Now, Viterbi algorithm is linear time. Okay, the amount of time it takes, the time complexity is linear in the length of n. We do not expect this because we are seeing that an exponential size tree gets constructed. So what makes it linear is the question. So let's understand that. Now, from hat, we go to V, and from V, we can go to V and N. From hat, we can go to N, and from N, we can go to V and N. So you see there are 4 paths here, and 2 paths end in V, 2 paths end in N. Okay. So here comes the crux of the Viterbi algorithm. All those paths which end in V, we observe them. And only that path which has the highest probability value is retained. All other paths ending in V are dropped. Similarly, observe all the paths ending in N, and the path which has the highest probability ending in N is retained, all other paths are dropped. This is the heart of the Viterbi algorithm. The reason is that from this stage, after looking at this Vn, Vn, whatever data comes in front of us, whatever words are coming in front of us, each of these paths, each of these partial paths will see all these words. Okay, it is not that one path will see a different set of words than other paths. All the paths will see the same set of words. Okay, and if since the observation is going to be same, and the accumulated probability values get multiplied, the paths which have lower probability have no chance of winning in the future. Okay, therefore those paths can be dropped. This is a consequence of the Markov assumption and the consequence of chain rule, the properties of joint probabilities. Okay, the probability of a path is the product of partial probabilities, and the observation sequence which comes after these states are reached are same. Okay, so paths which have lower probability can be dropped. Lower amongst what? Lower amongst all those paths which are ending in the same state. Okay, so this is the heart of Viterbi. Make sure that you understand this crucial point very clearly. Okay, so now the path hat VV is dropped. The path hat VN is also dropped. This, as per our intuition, in people dance, people should be noun. How can people be V? So that's why this whole top sub tree is dropped. Then we have to develop the path which was ending in N. Now the next word which is seen is dance. So you can go from N to V or N to N. Okay, so the accumulated probability is 0.8, and B1 and B2 are the product of probabilities, which is giving me 0.0016 and 0.064. The next token which is seen is the dot. So we have to consider the probability C1 and C2, which is nothing but the product of B2 into probability of dot given V into probability of dance given V. And C1 is B1 into probability of dot given N multiplied by probability of dance given N. Okay, so all these path probabilities have been computed, and we should be able to finally get the result. We can give equal probabilities to sentences ending in noun and verb. Also, dance as a verb is more common than noun. So probability of dot given N is assumed to be 0.5, which is equal to probability of dot given V. Probability of dance given noun is 0.001. Probability of dance given V is 0.01. These are our assumptions. Then we have to find out the C1 value. C1 value is coming out to be 0.000008. C2 value is coming out to be 0.00032. Okay, so these are the C1 and C2 values. And then we have been able to identify the most probable path, which is the C2, the one which is giving the C2 value, that value. So here the path will come out to be hat, N, and V. People is noun, dance is verb. So we have been able to disambiguate the whole sequence with respect to its part of speech. So sit down with the slides. You will see that the calculations are quite easy to follow as long as you are clear about the theory, which is product of probabilities based on Markov assumption and chain rule. So computational complexity. If we have to get the probability of each sequence and then find maximum amongst them, we would run into exponential number of computation. Okay. If S equal to number of states, that is the number of tags is S, tags plus hat and dot, and O is the length of the sequence which is given, the words. Then the number of sequences is s to the power O. Minus 2 you can forget, s to the power O. But a large number of partial computations can be reused using dynamic programming. And since we are dropping the paths, which have low probability value, at every word, we have to maintain only T paths. Okay, after every word, you have to maintain T paths. So T into the number of words is the complexity of the Viterbi algorithm. So what potentially seemed like an exponential algorithm has come down to be a linear algorithm. Okay? So these are some nitty-gritties which you should be able to understand very well looking at the slides. And also, there's lots of internet material on Viterbi and so on. But this particular example is very simple to illustrate the main idea of the Viterbi algorithm. And the key slide here is this slide. This slide. The slide where we are writing stopped. Okay, these paths are not advanced anymore. Okay, fine. So what are the problems faced in hidden Markov model part of speech tagging? All problems can be traced to only one problem. That one problem is sparsity. Following are the kinds of sparsity problem. There can be unseen words. So for example, in the training corpus, you have the word delay. And in the testing data, you have the word procrastination. Procrastination and delay mean the same thing. Okay. Different forms of the word, morphology. The corpus is predictable, and test corpus has, let's say, test data has unpredictable. Okay, so in the training data, I've seen predictable, but I have not seen unpredictable. It can have code mixing. So, आप मुझे advice दीजिए. So instead of saying आप मुझे सलाह दीजिए या परामर्श दीजिए, आप मुझे advice दीजिए. This is called code mixing. Two languages are mixed. So when you have code mixing, then the training data and test data can have this problem. You might not have seen all the words in the test data in the training data. And the corpus doesn't have the particular word and tag combination. For example, people as a verb is extremely rare. So in the training data, you probably have not seen people as a verb. So what to do about it? These are all sparsity problems. There are 4 kinds of sparsity problems I have noted down here. You can maybe think of other problems also, so which can be related to sparsity. So is it clear? The data-driven part of speech tagging, that is machine learning-based part of speech tagging, has the problem of sparsity. How to solve sparsity problem? You solve it by what is called smoothing. Okay, smoothing. So you read up on smoothing. There is a lot of material on smoothing. There are famous algorithms for smoothing called good Turing, Laplace, okay, add one smoothing. But best possible smoothing is these days done with the help of embedding. Now you see, delay and procrastination mean the same thing. So their vectors also will be same, almost same. So their cosine similarity value will be same, almost, and that can be used. Okay, I'm sort of jumping the gun. You will come back and ask, what is embedding? Embedding is a representation of the word in the form of a vector. And it suffices us for this moment. If the vector is, if the vector of a word is close to another word, then their cosine similarity is high. Okay. Now, 3 basic tasks we have seen. This is also a good diagram to illustrate the Viterbi algorithm and why it is not exponential. We'll look at this diagram later. Now we come to this question of probability of an observation sequence, that is computing the language model. So probability of an observation sequence is linked with the probability of the state sequence. Can you compute the probability of an observation sequence? You cannot directly compute the probability of an observation sequence because what is given to us is the transition probability. The probability of going from one state to another. What else is given to us? the observation probability of an observation given the state. So state always appears in the machine's description. Therefore, to obtain the probability of an observation sequence, we have to somehow bring in the probability of the state sequence. So, yeah. Yeah.
Why how is stored an answer point to in that path? There might be a probability that there might be point, and here after 0.6 the maximum comes out to be 0.
What is the question? After seeing dot,
Find out the maximum
yeah.
at every step. But then
okay, so let's talk about it after the class. Yeah. So now I just want to finish with this particular note. The importance of strictly following laws of probability. Okay, the importance of strictly following laws of probability. If you want to compute the probability of an observation sequence, in our case, the probability of a sentence, which is also language model, that cannot be computed without bringing in state. The way you bring in another random variable to compute the probability of one random variable is through a process called marginalization. So probability of O is equal to probability of O, comma S over all possible S. Okay, so this becomes then a summation of probability of O, comma S, which is joint probability, which is equal to probability of S into probability of O given S. So both we know, by the way. Probability of S, we can find out from transition probability table. Probability of O given S, we can find out from the observation probability table, right? So then, since both the parameters are given to us because of the hidden Markov model, we can compute the probability of the observation sequence also. The key point is how to compute the probability of the observation sequence efficiently. Again, there is a Viterbi-like algorithm. We can drop paths whereby we get more efficiency. So let me finish in 2 minutes now about the question of evaluation. So we'll be doing this assignment of part-of-speech tagging, and the first question we'll ask you is, what accuracy have you got for part-of-speech tagging? Now, any part-of-speech tagging system which does not cross an accuracy of 90% is not useful, because part-of-speech tagging feeds into parsing, semantic role leveling. Everywhere part-of-speech tagging plays its role. Okay, so we have to evaluate the accuracy of part-of-speech tagging, and this accuracy is evaluated by very well-established concepts of precision, recall, and F-score. Okay, we'll elaborate these concepts going forward. Many of you know, I'm sure many of you know what is precision, recall, and F-score, but there are a few, subtleties which I'd like to point to you. So precision and recall is expressed by this diagram. S1 is the set S1 is the obtained values, S2 is the actual values. The intersection between S1 and S2 divided by the size of S1 gives me the precision. The intersection of S1 and S2 divided by S2 gives me the recall. Okay, why so? And since precision and recall have an inverse relationship, if you increase one, the other decreases, you strike balance by computing the harmonic mean of precision and recall. Why harmonic mean is again another question. And the generalized precision score is F beta, which is 1 plus beta square into precision into recall divided by beta square P into R. Typically, precision recall are given equal importance, so beta is 1, in which case F1 equal to PR by P plus R, half into PR by P plus R. Sorry, 2 into PR by P plus R, which is the harmonic mean of the two values. Okay, why harmonic mean, we'll see. So this is the discussion on part-of-speech tagging, how it is computed, and how we measure the evaluation. So let's stop here today. Do remember, 29, there will be a quiz, and at the end of August, you'll have to demonstrate part-of-speech tag.